Okay, this is going to be the 6th video on how to find the volumes of solids using cross-sectional areas. And the problem we'll look at this time, it's similar to the one we did in the number 5 video, and it goes like this. It says, find the volume of a solid whose base is bounded by the region given by x squared plus y squared is equal to 9. And hopefully you'll recognize that as being the equation of a circle with radius 3. So the solid in this case is going to have a circular base. Then it says assume the cross sections are perpendicular to the x-axis, and in this case we'll say have the shape of an equilateral triangle. Now in the last video we worked almost the same problem, but the cross sections were in the shape of a square, so let's change it to an equilateral triangle and see what that looks like. Now sometimes the book will give you a picture. If it happens to give you a picture of it, the situation would look like this. So first of all, you've got the base of the solid is in the shape of a circle, so we'll go ahead and temporarily remove that cross-section. If you did x squared plus y squared is equal to 9 and sketched it in the xy plane, you'd have a circle that looks like this. Now the idea is you come out a certain distance over here, x, and put a baseline in, and this will be the edge of the triangle. And if you sketch just one section of that, one cross-section, it would look something like this. So the idea is you want to find out if you summed up all the cross-sections all the way across this, it would give you an object, and the solid object would look something like this green object right here. So again, the green object is composed of a series of cross-sections that look like this. And to help you picture it, let's go ahead and just temporarily remove that red axis. So what you want to find now is the volume of this green solid composed of these cross-sections. So we'll go ahead and put the axis back in, and let's temporarily remove the solid and just work with these parts right here. Okay, now we're going to follow the same steps that we've done in the previous videos, and if you haven't done it yet, I would definitely watch those previous videos. But let's take a look at the steps that we used, and they look like this. Now the first 2 steps just involve making a sketch of the problem. The last 4 steps involve setting up and evaluating the integral. So we'll run through these as we go through. And the first one says this. First of all, sketch the base of the solid in the xy plane using the boundary conditions. So let's see what that would look like on our problem. Okay, now what we've got, if the book gives you a 3-dimensional sketch, sometimes it's kind of hard to draw that on your page. So just like we've done in the previous videos, let's assume that we are going to make a kind of a 2-dimensional sketch over here, looking at this thing straight from the top. And this is the way I would sketch it on your homework page or if you were taking a test. So first of all, looking at the boundary conditions, x squared plus y squared is equal to 9 is a circle with radius 3. So draw a circle, and we'll go ahead and shade it in to see what it looks like. So this is going to be the base of the object. It's going to go from this side to be minus 3, and we go ahead and put that on there. So it goes from a negative 3 here. And I think I'll actually put that in black just so it'll stand out a little bit better. So we'll go a negative 3 over here to a positive 3, and that's going to be the radius of the circle. Okay, so we've got the base drawn. So we'll go back to our steps. The second step says this: sketch a single cross-section in the required geometric shape. So what we're going to do, basically, is the same thing that we've got over here. Now, the way this one was drawn is if we remove the cross-section, you come at a certain distance x and put a baseline. And we'll do the same thing over here. We'll come over a certain distance x and just put a baseline. Let's just say that it goes from here down to, and I'll say about right here. So this baseline right here represents the same thing as this one here. Then from that baseline, you draw an equilateral triangle. And the triangle would look like this if you saw it in 3 dimensions. And we'll roughly do the same thing over here with not quite as much detail. So what I'm going to do is just picture from here it goes up to the top, back down in the base. So I'll go up to the top, something like this, back down to here. And you also want to give it a little bit of thickness because you want to find the volume of this little section. So just like this one has an implied thickness, let's go ahead and put just a little bit of thickness on this. So this will wind up looking something maybe like this. It'll go down kind of like this. And finally across like this. So it's got a little bit of thickness to it, and I think I'll shade that just a little bit to make it a little bit easier to picture what's going on. Okay, so just roughly draw one cross-section. So on your homework page, the figure would look like this. The book picture might look like this, but these two now represent the same thing. So let's go back and take a look at our next step. So we've got the pictures drawn. Now to actually solve the thing, the first step is to find a general geometric formula for the given shape. So in our case, the given geometric shape was an equilateral triangle. So the next thing you need to do is to go into a geometry book, and if you look, you'll find the formula for an equilateral triangle. And the general formula for the area of an equilateral triangle you should find in a geometry book would be the square root of 3 over 4 times the side, whatever the length of the side is, squared. So this is the general formula for an equilateral triangle you should be able to find in a geometry book. So back to our steps. Now the next thing says this. You've got the general formula, but now you have to find a specific formula for your particular problem, and you've got to get it in terms of x, because eventually the integral will be in terms of x. And in some cases, this is the trickiest part of the problem. So let's see how that works. So what we've got here is this. Here's a formula for the area of this triangle. What it's going to give you is just the area, frontal area of that triangle right there, or if you prefer, this triangle over here. But you want to get it in terms of this specific problem. And to do that, this is where your picture comes in. Now what I would do is this. If you start at the origin and you go over here a distance x, if you go up, the coordinates of this point right here, this thing right here is going to be y. Now, as far as the side of the triangle goes, the distance from here to here is going to be the length of the side of the triangle. But what is that? Well, now, by your figure, by symmetry, if this distance is y right here, then by symmetry, this distance right here would also be y. So this total distance is going to be 2y. So the length of that side by our figure is going to be 2y. So to use that, take this and go ahead and put it back down to this general formula. So now this will change to the square root of 3 divided by 4, but now you know that the side is 2y. So in place of the side, the length of a single side is 2y squared. And we'll go ahead and expand this. This would be square root of 3 divided by 4. And if you square the 2 and square the y, you would have 2 squared would be a 4, and this is going to be y squared. And then finally, these two 4's will cancel out, and it will leave you with square root of 3 times y squared. And we'll scoot this down just a little bit. So what this is going to be the cross-sectional area. So the cross-sectional area for our problem, but the thing is, at this point, it is in terms of y. So in some problems, first of all, you have to get in terms of y before you can put in terms of x. So what I've got here, this is the cross-sectional area, but let's go back to our steps. And in our steps, we want the cross-sectional area, but we want it in terms of x, because you got to find the integral in terms of x. So the next thing to do, inside this step, you have to change that area in terms of y into an area in terms of x. So we need to change this y into an x. And to do it, we'll do the same thing we've done in the previous problems, is looking at the boundary conditions for the base, use this to express x in terms of y. So let's see what that's going to look like. So you've got x squared plus y squared is equal to 9. So I'm just going to come down here and start with that. So I've got x squared plus y squared is equal to 9. Now solve this for y. So y squared would be equal to 9 minus x squared, and then take the square root of both sides, and you get y would be equal to plus or minus the square root of 9 minus x squared. So what this is, if I put a little box around this part right here, this now gives me y in terms of x, and I can use this back over here in this part. So let's go ahead and do the following. Right now I've got the square root of 3, and now I know that y is the square root of 9 minus x squared. Now it's plus or minus, but I'm going to wind up squaring it anyway, so I can just put the square root of 9 minus x squared, and then it's squared, so this is going to be squared out here. Okay, in this case, the square and the square root will cancel out, so it'll leave you with the square root of 3 times 9 minus x squared. And what this is an expression for the area of the equilateral triangle, but in terms of x. So now you've got the cross-sectional area. So the cross-sectional area, but rather than having it in terms of y, now you've got it the way you want it. You have it in terms of x. So it's possible when you first set it up, you may come up with the initial cross-sectional area in terms of y, and then just use the boundary conditions to change it into terms of x. Okay, back to our steps. And we'll go back up here, and next step is determine the limits of integration. You can get this right off the picture. So looking at our picture, we're going to go from -3 to 3. It's all in terms of x. And by the way, the thickness of this thing, this little thickness right in here, that little thickness is dx. So I know that the thickness of this cross-sectional is dx, just like this little thickness right over here would be dx. Well, I'm going to integrate it from going from right here all the way across to right here. So I'm going to go from there to there. That goes from -3 to 3, and those are going to be my limits of integration. So back to our steps again. And finally, the last step is, now that you've got everything that you need, just to find the volume of the green solid, just evaluate the integral of the cross-section of a single cross-section times the thickness, which would be dx. So the area of the cross-section times the thickness of the cross-section will give you the volume of the cross-section. Sum them all up, and you'll have the integral. So let's go back and see what that looks like. Okay, so I want to come down, and I'll go a little bit lower here. I want to find the volume. So the volume is equal to the integral from -3 to 3 of the cross-sectional area in terms of x, which is this part right here. So the square root of 3 times 9 minus x squared dx. Now it's just a matter of evaluating that integral. And we'll bring it down just a little bit lower here. This one could be, now again, the square root of 3 is a constant, so I can go ahead and bring that outside. So the square root of 3 times the integral from -3 to 3 of 9 minus x squared dx. And if you evaluate this integral, you'd have the square root of 3. Then this would become 9x minus x cubed divided by 3, evaluated from -3 to 3. And if you plug in the numbers, then you'd have the square root of 3 times, I think I'll put it like this. This would be 9, and first of all evaluated at 3, minus 3 cubed divided by 3. Then plug in the bottom number, 9 times a -3 minus a -3 cubed divided by 3. And if you ran through all these numbers, I'll let you go through them. It'll turn out to be the square root of 3 times 36, which we'll go ahead and write as 36 times the square root of 3. And just so you know, that's approximately equal to about 62.35. So if you wanted exact, you would have this. If you wanted approximate, you'd have this. So the exact volume of this green solid is 36 times the square root of 3. And let's go back up and look at the picture again. Let's go ahead and put that green solid back on there. So, and I think I'll remove the axis in this case. So the volume of this green solid is 36 times the square root of 3. And again, run through the series of steps. We'll go ahead and put this back on. If you follow these two steps, the first two steps are to sketch them and come up with a single cross section, and then follow the other steps. And what that looks like over here was to, first of all, make this sketch and sketch in a single cross section. And you need that sketch to be able to change the general formula into a specific formula. Then the next step was to sketch a general formula, and in the most general terms, it looks like this. So just out of a geometry book, the area of a equilateral triangle is the square root of 3, 4 times the side squared. Then, in the next step, is change it from this general formula into a specific formula for your problem, but in terms of x. Now in this case, first of all, I found it in terms of y, and then used the boundary conditions to change it into a cross-sectional area in terms of x. Once you've got it in that form, then it's just a matter of plugging it into this formula. So the volume is just the integral of a single cross-section times the thickness of that cross-section. And if you evaluate that integral, then you'll have the volume of the green solid, and you'd have your answer. So that's a 6th video, and again, that was a circular base with equilateral triangles for cross-sections, and using the same 6 steps. And again, if you stay with these 6 steps, they make a pretty good guide for solving these kind of problems. So hopefully that helps you out just a little bit.